Very good morning to all and welcome to my class. Today we are going to discuss about the electrochemistry, right? So far we already covered, four chapter, that is mole concept, structure of atom, thermochemistry, and in last class we already discussed about the chemical equilibrium. So we already covered the four chapters. So in today class we are going to discuss electrochemistry. So this is one of the important chapter on the J point of view, right? Advanced point of view. So let's discuss about this chapter. I hope my voice is audible to you all and my screen is also visible. If you find any problem related to this, you can text me, right? Okay, so let's start with the today's session, that what we are going to basically study in this chapter. So basically, we all know what is electrochemistry. We quickly revise this thing because in one class we have to do all the important concept and PYQ question as well. So I am going to quickly revise this all these things so that you can able to learn this thing in a good way, right? So what is electrochemistry? So basically electrochemistry is the branch of chemistry which deals with the interconversion of chemical energy in the electrical energy, right? So basically in this the interconversion of chemical energy and the electrical energy will take place. Now, basically chemical changing, what is the chemical change involving? It means the flow of electric current, right? So flow of electric current are referred as the electrochemical change. Okay. So, electrochemical cell, or we say galvanic cell, or we say voltaic cell, right? So this one is very, very important and you must know, you must understand this. What do you mean by this term? Electrochemical cell or a galvanic cell or a voltaic cell. So basically in a galvanic cell, some spontaneous redox reaction takes place during the electric current, right? Basically in galvanic cell, a spontaneous redox reaction takes place during producing electric current, which in result produce electric current. That means in the cell, chemical energy is converted into electrical energy, right? It means in this cell, chemical energy get converted into electrical energy and so on. The change of chemical energy to electrical energy cause lowering of free energy, right? So the change of chemical energy to electrical energy cause lowering of free energy, which appears at the electrical energy and measured in terms of EMF, right? So they are measured in terms of EMF. In this cell, chemical reaction takes place in the two compartments, each of which is called half cell and contain a suitable electrolyte and electrons, right? So in this cell, a chemical reaction takes place in the two compartments, each of which is called a half cell and contain a suitable electrolyte and basically electron. Right. So basically, one important thing here in a galvanic cell or electrochemical cell, the function of salt bridge is very important because this salt bridge is used to connect the to connect the two solution, right? So these salt bridge are very important, so must understand what is salt bridge, what is its function and all, right? So basically the solution in the two compartment is connected through a salt bridge as we see in the diagram, right? So it is defined as the how will you, this is salt bridge, right? This K2SO4, this represent salt bridge. So this represents a salt bridge. So basically it is defined as the inverted U-shaped tube that contain a mixture of agar-agar jelly and electrolyte like KCN, KNO3 or ammonium nitrate. They are also called as a inert electrolyte, right? So these are basically the salt bridge and all. Okay, as we see in a two different beaker, in one beaker we have a copper rod which is dipped in the copper sulfate solution, and in the another beaker we have a zinc rod which is dipped in the zinc sulfate solution, and these two solutions are well connected through a salt bridge like K2SO4 solution, right? Later we are going to study the role of K2SO4 and all in a detail, right? So this is what the basic use of the salt bridge. Basically, it is used to connect the two component of the galvanic cell. Now, what is the significance of the salt bridge includes? What are the various significance? So basically, it connects the solution of the two half cell, thus complete the cell circuit. This one is also very important. It connects the solution of the two half cell, thus complete the cell circuit. It help in keeping the solution in the two half cell, electrical neutral. So this one is also important. The first one is it complete the cell circuit. Without salt bridge, the circuit won't complete it. And the second one is it help in keeping the solution in the two half cell, or we say electrical neutral. Next, it provides negative ion to the anodic half cell. Also remember this thing, it provides negative ions to the anodic half cell and thus preventing the accumulation of extra positive charge in the solution and around anode, which normally hinders the flow of electrons from the anode. So you understand the meaning of this, right? Because generally what happened, anode is a positive, right? So there's a large number of positive charge are accumulated near and the further movement will stop. So to avoid this, to preventing the accumulation of extra positive charge in the solution and around the anode, which is normally hinders the flow of electron, we use salt bridge because it provides negative ions to the anodic half cell. On the similar, the electrolyte should be inert and should not react chemically with the electrolyte of either of the two half shell. So one important condition here, the electrolyte that we use in the salt bridge are must be inert and should not react chemically with the electrolyte of either of the two half shell, right? The cation as well as the anion of the electrolyte should have the same ionic mobility, like, and almost same transport number. So what do you mean by this term have a same ionic mobility and the same transport number? It means, if I'm talking about KCl, so both K positive and Cl negative have a equal reactivity, they have a ionic mobility, means they have a strong tendency to go from one. If I'm talking about potassium, it having positive charge, so it have a strong tendency to go towards the negative, and Cl having negative charge, so it has also strong tendency to go towards the positive end, right? So in this term, the cation as well as the anion of electrolyte should have the same ionic mobility. Okay, so I hope this is clear to you. Now we can understand the Daniels. Okay, once we understand the salt bridge, so salt bridge is very much clear. It connects the circuit, it maintains the electrical neutrality, and it should be inert, right? So they are the basically the function of the salt bridge. Now let's study about the Daniel cell. So basically, an example of galvanic cell is a Daniel cell. So a galvanic cell is an example of Daniel cell itself. This cell is designed in such a manner to make the use of the spontaneous reaction between zinc and copper ions to produce an electric current. So basically, in this cell, we use the zinc and copper rod ions to produce the electric current, as we see in the diagram below, right? So the first one is a zinc rod in which they are containing a solution of zinc, right? And the second one we have a copper which is dipped in the copper sulfate solution, okay? And salt bridge is used which which complete the circuit, which join the two compartment of anode and cathode, right? And here we can see that the electron will flow from the anode to cathode, that is from the zinc to the copper, and direction of current is always opposite, right? Direction of current is always opposite to that of the electron flow, right? So this is how we can actually represent the electrochemical cell. So it is very much important for drawing any electrochemical cell. You must have two different rod, two different electrodes dipped in two different solution, and they are well connected through a salt bridge, or we say in which the electron flow from the anode to cathode, and we know that the direction of current is always opposite to that of the direction of electron. So the current flow from cathode to anode, right? So this is all about the electrochemical cell. Now, what is Daniel cell? Some important point regarding to Daniel cell. So, in Daniel cell, the anode is made up of a zinc rod and dipped in a solution of ZnSO4 oxidation half cell. This will make the oxidation half cell, right? Similarly, the cathode is made up of the copper rod and dipped in the solution of copper sulfate reduction half cell. When the zinc and copper electrode are joined by a wire, the following observation are noted, right? So whenever the zinc and copper electrode are joined by a wire, we observe the following observation. What are the observation, right? So there is a flow of electric current in the external circuit from copper electrode to zinc electrode that have a positive electrode to a negative electrode, right? So there is a flow of electric current in the external circuit from copper electrode to a zinc electrode, that is from positive to negative. The zinc rod loses its mass while the copper rod gain its, right. So the zinc rod loses its mass, zinc rod, because this is an anodic part, so they start losing their mass, while the copper rod gain its mass, right? And the concentration of ZnSO4 solution increases because more and more Zn will be converted into Zn2 plus ion, while that of the copper sulfate solution decreases because copper 2 plus accepting the electron, they convert it into the copper, right? So the concentration of ZnSO4 start increasing, where the concentration of copper sulfate start decreasing. The overall redox reaction in the Daniell cell is, for example, you can observe that this is zinc plus copper will react to give zinc plus copper. So here the oxidation of zinc will take place because here the oxidation number of zinc is what? Here the oxidation number of zinc is 0 and here the oxidation number is 2. So there is a oxidation, right? So there is an oxidation. So oxidation takes place. So we know that zinc undergo oxidation. Is it clear to you? Right? That is zinc undergo oxidation. Okay. Similarly, if I'm talking about copper, copper having oxidation state 2 here, and here the copper having oxidation state 0. So the reduction takes place in case of copper. So the half cell in which the oxidation occurs is called the oxidation half cell, while in which the reduction occurs is called reduction half cell. For example, zinc loses 2 electrons and it will form oxidation half cell. Similar, copper accept these 2 electrons to become copper, and this is called reduction half cell, right? So this is all about the overall redox reaction. Now, observe this. This one is very, very important, right? What is this, beta? So basically function of Daniell cell when the external voltage is applied. So when we apply external voltage, then three cases can maybe occur. And what are the three cases there? First is when the external voltage is equal to external voltage of the cell. Right. When the external voltage that we apply is equal to the EMF of the cell. That is the EMF which is producing by the cell. In this, the cell reaction will stop and current becomes zero, as we see in the figure A. In figure A, we know that in case of Daniell cell, the E cell is equal to 1.10 volt. If you exactly apply the same voltage of 1.10 volt, right? If the external voltage is also 1.10 volt, then no flow of electrons or current, or we say no chemical reaction will takes place. Now, when the E external is less than EMF of the cell, right? Then the cell reaction takes place as you see in the figure B. Basically, in this, the external voltage is less than the cell voltage, right? It means external voltage is less than 1.1 volt. So what happened basically in this? Electron flow from the zinc rod to copper rod, hence current flow from copper to zinc. Zinc dissolve at anode and copper dissolve at cathode. So this is the most used case of the Daniell cell, right? When the external voltage is basically less than the EMF of the cell. In this case, what happening? Electron will flow from the zinc to copper, or we say from anode to cathode, and electron and electric current will generally opposite of this, so it will flow from cathode to anode. That is from copper to zinc. Right. Now the next case, one more case is here. When external voltage of the cell is greater than the E cell, then the current will flow in the opposite direction and the chemical reaction of the cell is reversed. So basically when the external voltage you applied is more than the EMF of the cell, then what actually takes place there? Electron flow from the copper to zinc and current flow from zinc to copper. Zinc is deposited at the zinc electrode and the copper is dissolved at the copper electrode. So this is the function of the Daniell cell when the external voltage opposing the cell potential is applied. So remember these three cases, right? The three cases are the first when the E external is equal to E cell, then cell reaction will stop and current becomes zero. When the E external is less than E cell, then electron will flow from the anode to cathode or from zinc to copper, and the electron is opposite, that is from copper to zinc, right? And this the cell will work, right? And the next case when the external voltage is greater than the EMF of the cell, then the current will flow in the opposite direction, right? And the chemical reaction of the cell is reversed. So just remember this. This one is very, very important thing. Note, electrochemical cell may be reversible or irreversible. It is reversible when the exactly equal and opposite E external is applied, or by any other means the chemical reaction is reversed, right? So note, a electrochemical cell may be reversible or irreversible depending upon what is the external voltage you apply. Now, this question are coming JAM in 2020. So this basically this concept we can also use in the advanced type of question as well. So considering the following cell, identify the incorrect statement from the option given below for the above cell. Right. So we in this external voltage is applied, right? So if E external is greater than 1.1 volt, then zinc dissolved at zinc electrode and copper deposited at copper electrode. right? This is the case. Zinc dissolved at the zinc electrode and copper deposited at the copper electrode. If E external is equal to 1.1 volt, then no flow of electrons or current occur. So this is absolutely correct. And if E external is greater than 1.1 volt, then electron flow from copper to zinc. Is it true? When the E external is greater than 1.1 volt, then obvious electron flow from copper to zinc, right? This is also correct. When the E external is less than 1.1 volt, right? When the E external is less than 1.1 volt, then zinc dissolved at anode and copper deposited at cathode. So identify the incorrect statement. So which of the following is the incorrect statement for this? So we know that statement B is absolutely true. C is also true. D is also true. So which is the correct option, beta? That is, this option is only incorrect, right? That is option A. So you have to identify the incorrect statement for the following cell. So option A is the incorrect statement, right? Because when the external is greater than 1.1, then the zinc does not dissolve at the zinc electrode, right? Zinc dissolve at the copper electrode. Now, how will you represent a galvanic cell? So there is a representation of the galvanic cell, that how will you basically represent a galvanic cell. So for any galvanic cell, representation be like, you must represent their concentration and the salt bridge, and then how their molar concentration, so that you can easily represent the galvanic cell. So let's see how will you basically represent the galvanic cell, right? So, for representation of galvanic cell, right? Just wait, just wait for a minute. Yes. Okay. So, how will you represent a galvanic cell? The cell representation contain anodic half on the left hand side and the cathodic half on the right hand side. So this one is first important note here. The cell representation contain anodic half of the on the left hand side and the cathodic half on the right hand side. The anodic side of the cell is represented by writing metal or solid phase first, and then the electrolyte. In fact, cation of the electrolyte, right? So the anodic side of the cell is represented by writing metal or solid phase first, and then the electrolytic, right? And then the electrolytic, right? So remember this thing, that is in fact cation of an electrolyte. So first you need to represent cation. Now in the second step, and in the cathodic side, on the other hand, it is represented by the writing the electrolyte first, anion, and then the metal or solid substance. So we can represent, metal and cation are separated by the semicolon or the vertical line. So we can represent the galvanic cell like this. This is the, this is first the anodic part, that is Zn, Zn2 plus. Concentration 1 mole, salt bridge. This is cathode, copper plus 2 to copper. So this is how we can actually represent our galvanic cell. Okay. Good. Now, representation of galvanic cell is done. This is simple how we represent. Now, what is electrodes and their type? So, the various type of electrodes we have that we are used in this, right? So, electrode is the material which conduct electricity to or from cell due to the movement of electron. It may be taken in any form like wire, rod, sheet, etc. Right. So basically the electrode is the material which conduct electricity to or from cell due to the movement of electrons, or it may be taken in any form, right? It may be taken in any form like wire, rod, sheet, or etc. Electrodes may be classified further as inert and ejectable electron, right? And anode and cathode, positive and negative electrode, reversible and irreversible electrode, right? So so they are the basically the electrons and they are classified. So they are classified as a inert or attackable electron, anode and cathode type of electron, right? Positive and negative electron, reversible and irreversible electron. So this is the classification of electron, right? Now, what is this electrode potential? What is this electrode potential is called, right? So when a metallic electrode is dipped in its salt solution, a potential difference is developed between the electrode and the salt solution, right? So whenever the metallic electrode, for example, copper in case when they are dipped in the copper sulfate, or zinc when they are dipped in the zinc sulfate. So whenever the metallic electrode is dipped in its salt solution, a potential difference is developed between the electrode and the salt solution. The reason for the development of such potential difference is exchange of electrons between the atom of the electrode and the cation in its salt solution. Such potential difference is called electrode potential, right? Thus, we can say that the electrode potential is the measure of the tendency of an electrolyte to gain or lose electron in the half cell, or it is represented by E. So, I hope it is clear what is electrode potential. So, basically, when the metallic electrode is dipped in the salt solution, a potential difference is developed between the electrode and the salt solution. The reason for the development of such potential difference is basically the exchange of electron between the atoms of the electrode and cation in its salt solution. Such a potential difference is called electrode potential. Thus, we can say that electrode potential is measure of the tendency of an electrolyte to gain or lose electron in the half cell, and it is represented by nothing but E. So, how will you represent oxidation potential? So, basically, two type of potential we have, that is oxidation potential and the reduction potential. So, the tendency of an electrode to lose electron or to get oxidized is called oxidation potential, right? So basically the oxidation potential means the tendency of an electrode to lose electron or to get oxidized is called oxidation potential. Such an electrode is always negatively charged with respect to its salt solution. Similar, what is reduction potential? The tendency of an electrode to gain electrons, to get reduced is called reduction potential, right? So the tendency of an electrode to lose electron is known as oxidation potential, and tendency of an electrode to gain electron is known as a reduction potential. Such electrode is positively charged with respect to its salt solution. Or we say electrode potential of oxidation is negative of the electrode potential of the reduction. I hope this is clear to you. So the electrode potential can of the two type. Basically, the half cell reaction are always written as a reduction, half reduction, or they are potentially represented as the reduction potential. Right. The electrode potential depends upon the nature of the metal and its ion, concentration of ion in the solution, and the temperature. Right. So this is all about the standard electrode potential. Basically, the potential difference developed between the metal electrode and solution of its ion of unit molarity, that is having 1 molar solution at 1 atm pressure and 25 degrees Celsius, or say 298 Kelvin, is called standard electrode potential, right? The standard electrode potential is denoted by E naught. That is the standard electrode potential of zinc electrode denoted by E naught, Zn2 plus 2 Zn, right? So PtH2 1 gram 1 atm or H plus 1 molar per liter, or we say zinc having concentration 1 mole per liter. So this is called the standard electrode potential. Basically, when the concentration is 1 molar only, pressure is 1 atm only, and the temperature is 298. So at this point, basically they are called standard electrode potential. So this is how we can actually measure, right? Now the next thing comes, that is how will you measurement of electrode potential will take place, right? So basically the measurement of electrode potential. Okay, so measurement of the electrode potential. The measurement of absolute value of the electrode potential is not possible for a single electrode, right? Only the difference of potential between the two electrodes can be measured experimentally. It is due to the reason that oxidation or reduction cannot occur alone. Basically, oxidation and reduction occur simultaneously, right? So basically, the measurement of electrode potential means the measurement of absolute value of electrode potential is not possible for the single electron, right? Only the difference of potential between the two electrodes can be measured experimentally. And it is due to the reason that oxidation or reduction cannot occur alone. That is, oxidation reduction occur simultaneously, right? So measurement of electrode potential. So for indirect measurement of potential of an electrode, we couple the electrode with another electrode whose potential is known, right? And this electrode is called the reference electrode, right? This electrode is called the reference electrode. Now, as we know, the EMF as well as the potential of a reference electrode, the potential of the other electrode is determined, right? So basically for the indirect measurement potential of an electrode, we couple the electrode with the another electrode whose potential we already know, right? And this electrode is called the reference electrode. So we are going to study some reference electrode as well. Now, as we know the EMF as well as the potential difference of the electrode, reference electrode, the potential of the other electrode is determined, right? So basically, what is happening here? If I want to know the potential of individual electrode, right? That is the measurement of the absolute value of electrode potential is not possible. However, their relative value is possible. For example, if I know the electrode potential of this, so with respect to this pen, I'll calculate the electrode potential of the other pen, right? So the absolute value is not possible. Only relative value will find. This is due to the reason that the oxidation reduction cannot occur alone. That is, oxidation reduction occur always simultaneously. So let's see some reference electrode that we are going to study. So reference electrode, like first one that we use as a normal hydrogen electrode, also known as NHE. So basically the hydrogen electrode is the primary reference electrode as it is used normally to know the electrode potential of the half cell of the galvanic cell. Right. So basically hydrogen electrode is the primary reference electrode as it is used normally to know the electrode potential of a half cell of the galvanic cell. The reason for such a uses is that it can act as a cathode as well as anode with respect to the other electrode. And due to the following reasons, right? Like H2 will give 2H plus lose one electron, and this accept two electron to form H2. It means the electrode potential of NH is taken as zero and it is represented by platinum hydrogen atom or H plus 1 molar solution. The hydrogen electrode is constructed by bubbling H2 gas at a certain pressure over the sheet immersed in a 1 molar HCl solution. So basically what you need to remember from this slide only that hydrogen electrode is the primary reference electrode. It is used normally to know the electrode potential of the half cell of the galvanic cell. The reason for such use is that it can act as a cathode as well as anode. So it can act both as a cathode as well as the anode with respect to the other electrode. And due to the following reason, and we can say that it both having tendency to lose electron as well as tendency to gain electron. Thus, we can say that hydrogen we can use as cathode as well as anode. That's why use normal hydrogen electrode, right? The next one is C, that is standard hydrogen electrode. So a hydrogen electrode in which the pressure of H2 gas is maintained at 1 atm and the concentration of H plus ion is solution is 1 molar is called standard hydrogen electrode. The EMF of H3 is taken as 0.0 volt at all the temperature as we can show here, right? So here the H2 at we supply at 1 bar pressure and in the downward we have finely divided platinum coated on platinum foil, right? So this will produce a voltage. So always remember this. If you want to calculate any electrode potential of the any electrode, then we use a reference electrode like SHE. So if you couple the hydrogen electrode with the zinc electrode, and if the total value comes out to be 0.76 volt minus 0.76 volt, it means this is the potential value of a zinc only because we already consider hydrogen having a standard reduction potential value 0.0 volt. So if you consider if you connect hydrogen electrode with the copper electrode and if measure the potential through the voltmeter, if it's called 0.34 volt, it means it is totally the electrode potential of copper alone only because hydrogen we know it is having 0.00 volt. So this is how we can actually calculate the electrode potential of the other electrode, right? Now what is the important point to be remember here? The use of She is not convenience because it is difficult to maintain H plus ion concentration as 1 molar and the pressure of the gas is 1 atm. Hence, it is common to use calomel electrode as the reference electrode, right? So the use of SH is not convenience because it is very difficult to produce the H plus ion concentration as a 1 molar and the pressure of the gas is 1 atm. Hence, it is common to use calomel electrode as the reference electrode. So what is this calomel electrode basically? So it is the another generally used reference electrode, but it is comes in the category of the secondary reference electrode. Primary reference electrode is the standard hydrogen electrode, right? So in this electrode, a paste of mercury and mercurous chloride is placed at the bottom of the tube, as we can show here, right? As you can see here, like this is HDCl2 and HDP. So the basically in this electrode, a paste of mercury and the mercurous chloride is placed at the bottom of the tube over this paste. KCl solution is filled and a glass sealed platinum wires is used for the electrical contact. The potential of the electrode depends upon the KCl solution, right? On the basis of the concentration of the KCl, the calomel electrode is named differentially. If the KCl solution is saturated, the electrode is called SCE, that is saturated calomel electrode, right? So if it depends upon the basically the concentration of the KCl. So on the basis of concentration of a KCl, the calomel electrode is named differentially. For example, if the KCl solution is saturated, then electron is called SC, that is saturated calomel electron. Now we know how will you calculate the electrode potential, right? Now let's see how will you calculate the EMF of the cell. So basically in the electrochemical cell, the electrodes in the different half cell have a different reduction potential, right? So in the electrochemical cell, the electrodes in the different half cell have a different reduction potential. As a result of this, different flow of electron is seen from the electrode with the higher tendency to lose electron to the other electrode. This difference in electrode potential of electrode is called electromotive force or a cell potential of the cell. We know that reduction occur at the cathode and oxidation occur at the anode. Therefore, we can say that EMF, how we can calculate EMF beta? EMF is nothing but the reduction potential of cathode minus reduction potential of anode. Similar, EMF is equal to oxidation potential of anode, or we say reduction potential of cathode, or we can calculate that is the oxidation potential of anode minus oxidation potential of cathode. So this is the three way. By any way, we can easily calculate the EMF of the cell. So by using any three method, we can calculate. Generally, we use, the first one, that is EMF is calculated on the basis of the reduction potential value, right? So according to the reduction potential value, EMF can be calculated as reduction potential of cathode minus my reduction potential of anode. Someone say that this is this can also written as E naught right hand side minus E naught left hand side, right? Because we know that E naught right hand side and E naught left hand side, because we know that in right hand side we have a cathode and in left hand side we have a anode. So we can also calculate EMF of the cell like E naught RHS minus E naught LHS, right? Good. Now some important point for EMF. So how will you calculate some important points of for the EMF? So basically, if the two half cell are selected randomly for the purpose of constructing a galvanic cell, then on comparing the reduction potential of the two electrodes, the electrodes whose reduction potential has a greater positive value is made cathode and the other electrode is made anode, right? So if the two half cell are selected randomly for the purpose of constructing a galvanic cell, then on comparing the reduction potential of the two electrodes, the electrodes whose reduction potential has a greater positive value is made cathode and other electrode is made anode. Constructing the cell in this manner will always give a positive EMF. Otherwise, sometimes if electrode is chosen wrongly, the EMF will be negative. So always remember that the value of EMF is always comes out to be positive one. So if whenever the value will come negative, it means the selection of the electrode is done by you is very wrong, right? So always select the correct electrodes for calculating the EMF. Must know which one act as a electrode potential, which one act as a cathode, and which one act as a anode. So for the selection is very important. So basically, the important point is here: the reduction potential has a greater positive value is made cathode. So always remember this: the reduction potential. So if the two electrode having more electrode potential, like let me explain with an example. Let's see if we have a zinc, that is zinc plus 2 and zinc. This is called the reduction potential. Reduction takes place now, Zn2 plus 2, Zn0. Here the value is 0.76 volt. right? Similar, if we have another electrode of copper, that is copper plus 2 to copper, and the value is given as 0.34 volt, right? So out of this, if someone asks which will act as a cathode and which will act as an anode, then always remember this thing. The one who having a maximum reduction potential value act as a cathode, right? So the reduction potential has a greater positive value is made cathode. So out of this, zinc and copper, which will having a greater positive values, beta, obvious cathode having highest value, because anode, zinc having a negative value, right? So copper having the positive and more value than zinc. So this will make as a cathode. So this is act as a cathode, and the above one, that is the zinc, act as an anode. So this is how we can actually identify which will act as a cathode and anode. These values are provided in the question. So no worry. This question, the values, that is the reduction potential of the electrode, is already provided in the question. So on the basis of this value, you can identify which one act as a cathode and which one act as a anode. Right. So I hope this is clear to you. Good. So now how will you calculate EMF? So we know how will you calculate EMF. Basically, EMF of the cell is nothing but it is equal to E naught of cathode minus E naught of anode. Right. So this E naught of cathode minus E naught of anode. So how will you calculate? So E naught of cathode is what? That is 0.34 volt. Right. Minus this will equal to E naught of anode is nothing but it's equal to minus 0.76 volt. So it will comes out to be 76 and 480, 80, and this is 1110. So it comes out to be 1110 volt, right? So this is equal to 1.10. So sorry, 1.10, right? So this is comes out to be 1.10 volt. So this is positive value, right? So always constructing the cell in this manner, that will always give a positive EMF. Otherwise, sometimes if the electrode is chosen wrongly, then the EMF will become negative. Now, some important point for the EMF is like, if the EMF of the cell is positive, then the cell is said to be spontaneous or feasible or exogenic. Yeah, always remember. If the EMF of the cell is positive, then the cell is said to be spontaneous, feasible, or exogenic. If the EMF of the cell is negative, then the cell is said to be non-spontaneous or non-feasible, or we say endogenic. That is delta G is greater than 0. Now, reduction potential is taken as the standard potential. If electrode potential is given and nothing is mentioned, whether it is oxidation or reduction, it is taken as the reduction potential by default, right? So reduction potential is taken as the standard potential. So if the electrode potential is given and nothing is mentioned, whether it is oxidation potential or we say reduction potential, so always taken as a reduction potential by default. Okay, so let's see some question related to this so that you can easily understand this thing, right? So let these some question related to this only. So this is the example number 12 in which they are asking to you about the important thing here. That is, what do you mean by this term? For the cell Zn plus Zn2, this is the solid representation is given, right? So zinc having potential difference of minus 0.76 volt, which electron will give a maximum value of inert cell per electron transfer. So out of the following Au plus 3, Ag, Fe, Fe2, Fe2 through Fe, you have to identify which will give the maximum values, right? So let's see which will give the maximum values and all, right? So let's see the one by one. If I'm considering the cell that is a cathode and anode, right? So what is the E naught cell? So if you're considering the E naught cell in a first case, that is for in the first case, what we have, that is a zinc and the metal name is Au plus 3 Au, right? So let's see each and every one by example. So if I'm considering the first one, that is cell, since cell anode and cathode, so zinc act as an anode, zinc act as a anode, and the next is that is a Ag. So this Ag act as a cathode, right? So Ag act as a cathode. So what is the tendency of this? It having tendency like zinc having tendency to lose electron, right? So zinc having tendency to lose electron, like zinc wants to lose 2 electron. On the basis silver having tendency of accept electron. So they have a tendency to accept only 1 electron. So multiply by this 2. So this will give us 2 Ag. So what is the overall reaction? Overall reaction be like, this is zinc, right? This is 2Ag plus, this is nothing but zinc 2 plus, and this is called 2Ag, right? So what is the E cell for this reaction better? So E cell for the reaction is nothing but E cathode minus ENO. So what is cathode here? Silver. Value is already given 0.80 minus 0.76. So the values comes out to be positive. That is 1.56 volt. What is the question they are asking? They are asking which cathode will have the maximum value of E naught cell per electron transfer. So this is for 2 electron, right? This is for 2 electron. So E naught cell per electron transfer. Per electron transfer. So it is the value of the per electron transfer beta. So it is nothing. So it is equal to 1.56, right? And divided by 2. So it comes out to be 0.78 volt, right? So it comes out to be 0.78 volt. Always remember 0.78 volt. So on the similar basis, you need to calculate for all. So you get to know this having the maximum value, right? So only A having the maximum value. If you're calculating for zinc and Fe, you'll get the value like 0.16. So this is for the maximum. So for rest all option, rest all three, that is for the AU, NFE, you need to calculate. You'll get to know this is the maximum. For AG, we have a maximum, right? So this is how we can actually calculate. Now, this thing is also very, very, very important. That is electrochemical series. So what is this electrochemical series is basically? So basically, the arrangement of metals in a decreasing order of tendency to lose electron is called electrochemical series. So basically, how will you represent electrochemical series? That is the arrangement of metals in a decreasing order of tendency to lose electron is called electrochemical series. It is the series in which the elements are arranged on the basis of their standard reduction potential value. So in this series, the electron elements are arranged on the basis of their standard reduction potential values only. Okay. Now, as we see in the graph, so this is basically the graph of the electrode potential series, right? So how will you actually represent this thing? Okay. So basically the standard electrode potential at 25 degrees Celsius, this is given. So this is the element like lithium, sodium, potassium, calcium, sodium, magnesium, aluminum, zinc, chromium, Fe, cadmium, and so on. And this is their reaction. Basically, the reduction is going on. And in the next column, we have a value of the standard electrode reduction potential value. So for lithium, you can observe that this is maximum. So maximum reduction potential value is for lithium, right? This is maximum. Similar, one important note here is hydrogen. So for hydrogen, it is zero. This is for hydrogen, right? So remember one important note here. Above hydrogen, all having negative electrode potential value. So above hydrogen, all having negative electrode potential value, and below hydrogen, all having positive electrode reduction potential value. As we can observe from this, from this series, from this electrochemical series. So hydrogen is the neutral point where value is reduction potential of nitrogen 0.01. We already assumed this. Above hydrogen, all the electrode having reduction potential value is in negative, and below all are in positive. Always remember. As we move down the group, as we move, let me first understand what happened when we move upward, right? That is from F2 to lithium. So we know that reducing character increase. So the reducing character increase. So if we move from bottom to top, reducing character, or sometime it is called reducing property. So reducing character or property increases, right? When we move from bottom to top. Similarly, when we move from top to bottom, then oxidizing nature will increase. Oxidizing nature. Done. Then oxidizing nature will be increased. So moving upward, reducing character increases. Moving downward, oxidizing nature increases. So this is how we actually represent this thing, right? How to arrange according to the reducing character, how to arrange according to the oxidizing nature. I hope you understand this thing, right? Similarly, if someone asks out of uh, lithium, potassium, sodium, they all are good reducing nature, right? Similarly, F2, AU, Cl2, bromine, they all are good oxidizing in nature. So remember this thing well, always. So basically, the negative sign of SRP, standard reduction potential, indicate that the electron, when joined with SHE, standard hydrogen electron, behave as a anode. That is, oxidation occur at the electrode. So basically, what is the negative sign of the SRP? Basically, if someone having the negative sign of the SRP, standard reduction potential, this indicates that the electron which joined with SHE, standard hydrogen electrode, behave as a anode. That is, the oxidation occurs at the electrode, right? Similarly, the positive sign of SRP, standard resistance potential, suggests that the behavior of electrode at the cathode when joined with SHE. The above statement suggests that the element which are a better reducing agent than hydrogen get their place above hydrogen. Right. The above statement suggests that this is very important note here. This above statement suggests that the element which are a better reducing agent than hydrogen get their place above hydrogen in the series. Such element have the negative value of SRP, while the element which are a better oxidizing agent than hydrogen get their place below the hydrogen in the series. Such element have a positive value of their SRP. Right. So these are basically the characteristics of the electrochemical series. Now, element which get oxidized easily are a good reducing agent, that is metals. And the element which get reduced easily are the good oxidizing agent, that is non-metal. A metal with the lower SRP can have the ability to displace metal with the higher SRP from their solution. While secondly, the reactivity of the metal decrease from top to bottom in the electrochemical series. Metal higher in the series are more active than the metal lying lower in the series. Right. So these are basically the fact. That is the reactivity of the metal decreases from top to bottom in electrochemical series. Metal higher in the series are more active than the metal lying lower in the series. So this point you must remember. Now, this question is basically from the electrochemical series itself. So oxidizing power of this species will be increased in the order. So you need to calculate the oxidizing power. So we know that when you move down the group, oxidizing power will be increased. So as the SRP become positive, so as the SRP become positive, oxidizing property also increases. So out of the following which having the more maximum positive value, that is 1.81, that is CO3. So CO3 having a higher oxidizing property. So CO3 is maximum. After CO3, we have a PB4. So CO3, PB4. After PB4, C3, and then Bi3. So option B is absolutely correct. So this is totally based upon the value, positive value, that is oxidizing power. So oxidizing power basically increases down the group, right? And the reducing power is increases from top, bottom to top. So now we are going to study the Nernst equation because this one is very, very, very important in a point of view. So what is this Nernst equation? So basically a relationship between the electrode potential and the concentration of the solution is called the Nernst equation. Because what is happening here? Because when you calculate the reduction potential SRP value or standard reduction potential, then it is a important point to note here that we calculate standard reduction potential only for those solutions which having the concentration of the 1 mole and which is takes place at the 25 degrees Celsius of temperature. But this case is not everywhere is useful. Somewhere we want some different cell having some different concentration, having some different which act as a different which we can make at some different temperature as well. So for this we cannot always dependent totally on only standard reduction potential because we want to make a cell having different concentration for the different purposes. So for this we use the Nernst equation because Nernst equation, by using Nernst equation we can actually prepare a cell having which produce the standard reduction, which produce the reduction potential having any other concentration than 1 molar, any other temperature than 25 degree, right? So it is basically a relationship between the electrode potential and the concentration of the solution is called Nernst equation. Now for the general reduction half reaction, we can write as this one. Like M, which when electron, they accept electron, they will be coming to M solid. So next equation for the given reaction we write as EM slash M, that is the reduction. And this is the standard reduction that we already know, that is cathode minus anode, right? This one we already know, cathode minus anode is equal to minus 2.303 RTNF log M upon Mn equals. We know the value of R, we know the value of F, and we know the value of temperature. If the temperature is given, then we can easily calculate EM, right? So since the concentration of the solid phase is taken in unity, the next equation will become like this, right? So this is the their modified form, because we already know that M is solid, that is the concentration of the solid phase is taken as unity, right? So for the hypothetical redox reaction, let us assume for the redox reaction that the M dash Mn is converted into Mn plus M. So for the electrical potential for the two half cell are given. So this will become like this. This is one for cathode and one for the anode. Now, in oxidation half cell, if the concentration of Mn plus increases, E oxidation also decreases. E oxidation decreases. If the temperature increases at the constant Mn, E oxidation start decreasing. Similar in the reduction half cell, if the Mn plus increases, E reduction increases. If the temperature increases at the constant Mn, then E reduction start increasing. We know that the cell potential, that is E cell, is equal to EMN, cathode minus anode, that is E cell is equal to cathode minus anode. Just put the value, that is E cell is equal to E naught cell minus 2.303, this one. And just put the value of F and R and D as well. If the reaction is at 25, then what we'll get? On putting the value, we'll get E cell is equal to E naught cell 0.0591 upon N log Mn aqueous X upon Mn aqueous Y, right? This is the concentration of the product. Or we better we can write concentration of the product upon concentration of the reactant. So this is how we can actually write this thing, right? I hope this is clear to you. So this formula we are going to use, right, for solving numericals. Only this formula, that is EMF of the cell is equal to E naught cell, and we calculate E naught cell by E cathode minus E anode, and thereafter 0.0591 upon N, where N is the number of electron, and this is the concentration of the product and the reactant. So this is how we can actually calculate this. Now, electrode potential of magnesium electrode varies according to the equation, that is E magnesium is equal to this one minus 0.0592 log mg. The graph of EMG versus log mg2 plus. So you have to predict the graph of concentration of M2. We already discussed this thing versus EMG. So what the relation we get, that this is, we already get the relation like now. If the M is increases, then the E oxidation start decreasing, right? So we get the inversely relation, right? So we get the relation like which is in reversible in nature. So out of this, which of the following graph is correct, beta? Understand this thing? Right. So if you consider equate this equation, like we know the what is the equation of the straight line? That is nothing but y is equal to mx plus c time. Right. This is the equation of the straight line. So the graph this versus log m plus 2, right? Versus log m plus 2 is a straight line with the slope of this, right? So this is the slope. We can compare this. On the y-axis we have a e mg plus 2 mg, right? C we have a like, and slope we have a minus 0.0591 upon 2, and this is log 1 upon m plus, right? So this is log 1 plus mg plus. So this is for the log 1 plus mg plus. This is all. So this is how will you actually, so this is the straight line with the slope of this, and intercept is E naught mg plus. So the correct equation for this, only in this curve we'll get the graph like this. So this is the slope from here to here. So this is the slope and this is the graph. So equation B is the absolutely correct relation for this, right? That is, this is the electrode potential of the magnesium electrode. So we can draw this graph by using this equation. Now, how will you determine the pH of the solution? So how will you determine the pH of the solution basically, beta? So using a suitable reference half cell, pH of the unknown solution can be determined. For example, for the particular reaction, that is H2H, platinum X, and Cl concentration is given. So left hand side of the reactions become this. It will what they are losing electron, and the right hand side they're accepting electron. So overall reaction like this. So we know that E naught, E cell is equal to E naught cell 0.9 log H plus concentration. So what is this H plus? So this is nothing but pH. So pH comes out to be E cell minus of reference. So pH is equal to E cell minus E reference upon 0.0591. So this is how we can actually calculate. So you can calculate the potential value of the hydrogen electrode by just the pH. So just using this formula in the downward this one, right? You can actually calculate this. Now, so let's apply Nernst equation for a concentration cell. So we are going to study the application of the Nernst equation, and we apply Nernst equation for the different cell. Now, first the Nernst equation for the concentration cell. So basically the cell in which the both electrode are of the same type, but the electrolytic solution have the different concentration, right? So those cell, basically the cell in which both the electrodes are of the same type, but the electrolytic solution have a different concentration are called concentration cell. You always remember. Basically, they are the cell in which the both the electrode are of the same cell. Both electrode are same. That is, we using in the one beaker we have a zinc, another beaker we already have a zinc. But the electrolytic solution have a different concentration. That's why they are called concentration cell. So when the electrode is reversible with respect to a cation, that is Z and Z2 plus having concentration C1, Z2 plus to Zn having concentration C2. So at anode, we know that what is happening, it loses two electrons, cathode, they accepting two electrons, and they will form like this. So obviously, the electrode potential is zero because we know that the electrode potential of the zinc is always 0.76 volt. So the electrode potential of this cell is zero. So if the electrode potential of the cell is zero, what is E cell? E cell is nothing but 0.0591 upon N, and the concentration is log C2 upon C1, where E naught is the 0 volt. Thus, for the reaction to be spontaneous, C2 must be greater than C1. If C2 is greater than C1, right? If the C2 is greater than C1, if C2 is 3, then it must be 2. So if the C2 is greater than C1, then the cell is spontaneous only. So this condition you must remember, right? This one is very important condition. Similarly, when the electrode is reversible with respect to anion. So this is the case when the electrode is reversible with respect to the cation, and this is when the electrode is reversible with respect to the anion. Let's say PtCl2, Cl, C1, Cl2 having this. So this having one. So each cell is nothing but 0.059, but concentration of C1 upon C2. So for such cases, all the reaction is spontaneous in forward reaction if C1 is greater than C2. The third case is when the electrode at a different concentration are dipped into the same electrolytes. Right. So when the electrode at a different concentration are the same in the same electrolyte. So two half cell, that is platinum hydrogen HCl and platinum hydrogen. So two half cell are joined by the salt bridge since they have the common electrolyte. So at cathode at anode, that reaction is like this. So we can write E cell is nothing but E naught cell minus 0.0591 upon N log P2 by P1. E cell is always equal to 0. So cell reaction is spontaneous in the forward direction if the pressure of left hand side is greater than pressure of the right hand side. Now, how will you find equilibrium constant by using the Nernst equation? So this one is also very important. That is the equilibrium constant from the Nernst equation. So we know that at equilibrium, EMF of the cell is zero. That is concentration of Cc into dt is equal to Kc. Therefore, the Nernst equation will be written as E naught cell is equal to 0.0591 upon N log Kc, where Kc is the equilibrium constant, right? So this is how you can actually determine the value. So this is a very important example, right? So this example is basically from the concentration cell. So what is the concentration of the Cl negative ion in the saturated solution? So chlorine negative having 1 molar HgCl2 Hg liquid, and chlorine is saturated HgCl2 Hg. And E naught is given, E cell is also given. What is the concentration of the Cl negative ion? Right. So we can actually calculate this. How we'll calculate this beta? Basically, the half cell of the reaction is given like half cell reaction, right? So half cell reaction is like when Hg2 Cl2, they accept this two electron to become 2 Hg plus 2 Cl negative, right? 2 Cl negative. What is Kc here? So Kc is nothing but Cl negative square, right? Now for the saturated solution of Cl negative, E naught is given and saturated half cell E naught is also given. So we know that this is for E cell is equal to E naught cell minus 0.0591, right? 0.0591. And this will nothing but it is equal to upon n. N is nothing but 2. This is log and concentration of this Cl minus 2. Done. Put the value. It is already given. This is 0.244. It is already given. This is 0.270. And this will comes out to be how it comes out to be. This will comes out to be 0.0591. This is log concentration of chlorine negative ion. So on we solving, so we'll get the concentration of chlorine ion as 2.754 molar. So this is basically the concentration of this 2.754. So it is the option correct. That is the C. So next is what is the relationship between the cell potential and the Gibbs energy changes? So basically in the electrochemical cell, maximum work done delta G is given by delta G is equal to NF into E cell, where F is the Faraday constant and is the number of moles of electron transfer. A galvanic cell does not electrical work by transferring an electrical charge through an external cell. When the small amount of current is drawn from the cell, then delta G negative become work of electron. So, if the delta G of the system is positive, then the process would be possible only if the surrounding do electrical work on the system, as in case of electrolysis. As delta G of the system is negative, then the system does electrical work on the surrounding, as in the case of galvanic cell. So, for the volatile cell, work is done on the surrounding, thus given negative sign. Hence, delta G is equal to work effect, which is equal to minus NFE naught cell. So, we can relate this. Delta G is nothing but it is equal to minus F E naught of the cell, right? So this is the concept which question related to this. So given that the standard potential or we say E naught of the copper and copper plus 2 copper are given, that is 0.34 volt and 0.5222 volt respectively. The E naught of copper 2 plus 2 copper is, so basically the half reaction we obtained copper to say copper and this to this. So we can actually, by knowing the values, we can easily calculate this, right? So we know the value of this, that is already this values is given. So just by putting the values, we'll get the answer for this. Now, this question, this is very much similar type of question. So you will try this question. Now, the next is relation between the cell potential NF into log Kc, where n is the number of moles of electron transferred in the valence equation for the process to which you apply the Nernst equation, right? So this question is from this. So question number 19 is basically from this topic only. So just you know the formula, just apply here. Given the equilibrium constant Kc of the reaction, if the E naught cell is this, right? So Kc is given, calculate E naught cell. So we know the formula, like what do you know, that is EMF of the, no, EMF of the cell, right? So EMF of the cell is equal to 0 at case of equilibrium, right? So equation become EMF, standard EMF of the cell is equal to, right? Standard EMF of the cell is equal to 0.0591 upon n, and this is equal to log Kc. So we know all the values like 0.0591, and what is n here? So we can observe that is n is nothing but 2 here, right? So n is 2. Just put the value log Kc. What is the value of Kc here? That is 10 into 10 to power 15. So just solve this, you'll get 0.473 volt, right? So 0.73 volt, which one is correct? 0.473, 0.473, right? No. 0.73 volt is coming now. 0.473 volt. So A is correct. This is in millivolt. This is wrong, right? So only A is correct at the formula. So this is the relationship between the standard potential of the half cell containing a metal in a different oxidation state. So if the two half cell having the potential of E1 and E2 are combined to a given third half cell reaction having a potential E03, then we can write delta G is nothing but G1 plus G2, or we say E03 comes out to be N1 E1 into E2 upon N3. So this is how we can actually calculate. This is the variation of the EM of the cell with the temperature. So using the Gibbs-Hamilton equation, the temperature coefficient of EMF of the cell is written as delta G is equal to delta H plus T into D delta G by delta T as a constant pressure. So delta G is equal to minus NF, just put the value. So you'll get delta H is equal to minus NF is T into D by D. And similarly, entropy change can be also determined by using this. Right. So this is all we covered the Nernst equation, electrochemical cell, salt bridge, and all this thing. Now, the one important thing also here is battery. So let's discuss about the battery. So basically, a cell or a battery arrangement of one or more cell connected in a series is basically called a galvanic cell. So basically, a cell or battery that is arrangement of one. If the arrangement of only one is there, then it is called cell. If the more than one cell is there, that is known as battery. It's basically a galvanic cell. It is used where the chemical energy of the redox reaction is converted into the electrical energy. So they are basically used when the chemical energy of the redox reaction is converted into electrical energy. So basically we classify them as a primary, secondary and type of battery. So just give me 2 minutes till I take some water, till try to read this thing because this is very simple. Okay, so let's discuss about the primary batteries. So what is this primary battery basically are? So basically the primary batteries are those in which the cell reaction occur only once. The battery become dead after use over a period of time and cannot be reused again. That is dry cell like a Lilith cell, mercury cell. These all are the example of the primary batteries, right? Now, Leland cell. So let's discuss about the very simple cell that we are using in our household lives. So it is commercial dry cell containing a graphite carbon cathode and in a zinc container as anode, right? So it is basically a commercial dry cell that we are using. They are containing a graphite carbon cathode in a zinc container and anode. NH3 formed in the reaction at a cathode combined with zinc to form a complex like tetraamine zinc, right? The cell has a potential is nearly about 1.5 volt. So the electrode reaction for the lamp cell is given as at anode. We can see that at anode the reaction takes place. Zinc oxidation takes place. So zinc loses two electron. And in cathode, amino 2 plus 2 NH3, they will accept this electron to form NH3. Right. So these are the basically the structure of in which the inside rod that is made up of carbon rod, which is acted as a cathode, and the outer surface that is the made of a zinc. Right. This is known as anode. And the paste of amino 2 ammonium chloride paste AR used in the dry cell. Okay. Now the next one is mercury cell. So basically, what is the mercury cell is? Basically, the cell potential of this mercury cell is about 1.35 volt, right? And it remains constant throughout its life. Since overall reaction does not involve any ion, the concentration of which can be changed during its lifetime, right? So the cell potential is approximately about 1.35 volt and remains constant throughout its life. And they remains constant since overall reaction does not involve any ion, the concentration of which can change during its lifetime, right? It means their concentration of which that cannot change during its lifetime. So let's see the reaction that's occur in the mercury cell. That is basically anode. They are using zinc mercury amalgam, and cathode they are using the paste of MgO and C. Right. So basically, what electrolyte are used in the mercury cell? That is a paste of KOH and zinc oxide. So paste of a KOH and zinc oxide are used as a electrolyte. Reducing agent like zinc and oxidizing agent like HgO. So it show the following electrode carry action like at anode, zinc mercury amalgam, that is zinc amalgam 2 ways they will give 2 electron and at cathode at mercury oxide accept this 2 electron to form Hg liquid or 2OH, right? So this is all. So now, what is secondary battery? Right. What do you mean by the term secondary battery? So basically, a secondary battery can be recharged by passing current through it in opposite direction so that it can be used again. Okay. So basically, a secondary battery can be recharged by passing current through it in opposite direction so that it can be used again. Okay. So a secondary battery can be used again and again. Okay. Let's see. So they are the lead storage battery basically. The most important secondary cell is lead storage battery, commonly used in the automobile and inverters. Basically, a 12-volt lead storage battery or the lead accumulator generally consists of a six cell, each producing 2 volts. Anode, which is made up of a lead, and cathode is made up of the grid of lead packed with the PbO2 as the cathode. Now, what electrolyte we use here? That is the 38% of solution of H2SO4. So here we use this is as a anode and this one is as a cathode, and this we use as a 38% of sulfuric acid solution. Negative plates, that is a lead grid filled with the strongly leaded. Positively plates, that is lead grid filled with the PbO2. This is the all about the lead storage battery, right? So basically, the overall reaction for the lead storage battery during the discharging when cell is in not use is basically anode, that is Pb. This is for discharging during discharging. So just need to remember one reaction during discharging. Just reverse of this, you'll get the reaction during the charge, right? So the overall reaction for the lead storage battery during discharging when the cell is in the use, that is anode. At anode, Pb react with sulfate to form PbSO4 and they loses two electrons. Similar, cathode is made up of lead oxide. So lead oxide react with sulfate and this will accept two electrons to form two PbSO4 plus 2H2. So the overall reaction of this cell is, as we can see that the overall reaction is like nothing but two electron get cancelled and just add this thing. Similar reverse reaction can occur when the cell is charged, like PbSO4 loses two electrons to become Pbs plus plus. Just reverse of this reaction, right? Just the reverse of the first reaction. So this is the total overall reaction we'll get and will represent the cell representation like Pb, PbSO4, H2SO4, PbO2. So this is how we can actually represent the lead storage battery. The next secondary battery is the nickel cadmium battery. So this is also a very important secondary battery. And this is a nickel cadmium battery with a longer life, but more expensive. So a nickel cadmium battery is a jelly roll arrangement and separated by a layer soaked in the moist sodium or potassium. So basically in this, the anode part is made up of cadmium and cathode is made up of metal grid containing NO2 immersed in KOH solution. Here the electrolyte used is KOH. The overall reaction of the nickel cadmium battery is when the cadmium react with two nickel hydroxide, it will form cadmium oxide and nickel hydroxide plus H2. Right. So the next one is the fuel cell. So this is also very important battery that we are using fuel cell. So basically the galvanic cell which are uses energy of combustion of fuel like H2, CH4, CH3, OH, etc. as the source to produce electrical energy are called fuel cell. So basically what are fuel cell? So basically are the galvanic cell which use energy of combustion of fuel like H2, CH4, methanol, etc. as the source to produce electrical energy are called fuel cell. One of the most successful fuel cell use reaction of H2 and O2 in gaseous state to form water. Right. The electrode reaction for the cell are as follow, like cathode and anode. So in cathode, O2 react with 2H2O and 4 electron to form 4OH negative ion. Anode 2H2 react with 4OH to form 4H2O, that is release 4 electron. So the overall reaction for this cell being 2H2 plus O2 will give us 2H2O, that is in liquid form. Right. So what are the advantages of the fuel cell? Can you tell me some advantages of the fuel cell? Like due to continuous supply of gases, such cell never become dead. So such cell is never dead because in this continuous supply of gases will be taken place. Usually they are operated at the 70 to 140 degrees Celsius. So they are operated between this much of temperature. High efficiency than other power plants, basically the 70% they having efficiency around 70%. And they are also pollution free. So these are the some important. Now remember, theoretical thermodynamic efficiency, how will you consider? That is efficiency of the fuel cell is nothing but it is equal to delta G upon delta H. minus NFE upon delta S. So basically they are the how will you calculate the efficiency of the fuel cell. Now let's see some disadvantages of the fuel cell. Basically electrolyte cause corrosion. So in this we use electrolyte which may be cause corrosion. Difficult to make contract between gaseous fuel, the liquid electrolyte, and the solid catalyst. So it is very difficult to make the contact between the gaseous fuel, the liquid electrolyte, and the solid catalyst. High cost of catalyst is the another problem. Gaseous fuels are difficult to handle at the low temperature and the high pressure. So uh, these are some the basically the problem that we are facing. Right. So we already discussed all this thing in a very detailed way. Right. Let's see some electrolysis and its law also. So basically electrolysis, it is defined as the process of decomposition of electrolyte by passing electricity. So this is opposite of the electrochemical cell. Electrochemical cell, we get the energy from the chemical reaction. Here, we need electricity for the chemical reaction to be occur, right? The apparatus used to bring about the electrolysis is called electrolytic cell. So basically, they are called electrolytic cell. There are mainly two ways in which the analysis is done in electrolysis: quantitative electrolytic study, or we say qualitative electrolysis. So basically, in the quantitative aspect of electrolysis, we use the Faraday laws, right? So basically, Michael Faraday studied about the relationship between the amount of current passed and the amount of substance liberated at the electrode during the electrolysis process. He gave the two laws which are known as Faraday laws, right? So this is the Faraday first law. According to the Faraday first law, the amount of any substance that is deposited or liberated at any electrode is directly proportional to the quantity of electricity passed through the electrolytic solution. That is W is equal to nothing but ZIT, where W is the weight of the substance deposited, Z is the photo proportionally constant, also called the electrochemical equivalent, I is the current, and T is the time. Right? Where 96,500 is called Faraday constant. Similar, what is Faraday's second law? That is Faraday's second law of electrolysis states that when the same quantity of electricity is passed through a solution of a different electrolyte connected in series, the weight of the substance produced at the electrode is directly proportional to their equivalent weight. That is, weight of copper deposited is equal to weight of the Ag deposited, which is equal to equivalent weight of copper upon equivalent weight of the Ag. The above formula can be given when the copper sulfate and AgNO3 solution are connected in the series and the same quantity of electricity is passed through. The requirement of electricity or charge is electrode reaction of oriented and varies with the change in the electrode reaction as follows. So, what is the conductance in electrolytic solution? The power of electrolyte to conduct electric current is called conductance or conductivity. Just like a metallic conductor, electrolytic solution also obey Ohm's law, which indicate the current flowing through a conductor is directly proportional to the potential difference across it. So we get the different formula like resistance. We get the formula of R is equal to V upon I. Conductance is nothing but they are the reciprocal of the resistance. And specific resistance or resistivity is nothing but rho, which is equal to 1 upon conductivity. Cell constant is also defined. L upon A is known as the cell constant. And this has a conductivity. So conductivity is reciprocal of resistivity. So you know the value of L, we just put the value, you'll get this. So what is molar conductivity? So basically the conductivity power of all the ions produced by dissolving 1 gram mole of an electrolyte in solution is called molar conductivity of the solution, and it is related to the specific conductance as like this. So molar conductivity sometimes denoted by lambda m or mu, which is equal to K into 1000 upon m, where m is the concentration in mole per liter. That is molarity of the solution. Its unit is either ohm inverse centimeter square mole inverse, mole centimeter square mole inverse, or Simon centimeter square mole inverse. So you can write in any way. Right. Now, what is equivalent conductivity? Basically, the conducting power of all the ions produced by the dissolving 1 gram of equivalent of an electrolyte solution is called equivalent conductivity. It is denoted by lambda eq or cap. It is related to the specific conductance as follows. Right. So, where CEQ is the concentration of solution in the equivalent liter, and its unit is ohm centimeter square, or we say mole. So what is the effect of nature of electrolyte over the conductivity? So basically the conductivity of an electrolyte depends upon the nature of the electrolyte, as the conductivity of the strong electrolyte is higher in comparison to the weak electrolyte. The reason for such difference is due to the difference in the ability of the ion present in their solution. Strong electrolyte dissociate completely, hence more ions are present in their solution, resulting to a higher conductivity. Weak electrolytes, on the other hand, dissociate less, hence less ions are present in their solution, resulting to a lesser conductivity. Basically, both the weak and strong electrolyte, the electrolytic conductance, the electric equivalent conductivity, and the molar conductivity increase with the dilution. So for the both weak and strong electrolyte, they are increased with the dilution. This is because the total volume of the solution containing 1 gram equivalent or 1 mole of electrolyte also increase. It may be noted that the decrease in conductivity on dilution of solution is more than is compensated by increase in flow. But one important note here, that is conductivity, or we say specific conductivity, will always decrease with dilution. Thus, for both weak and strong electrolyte, this is due to the fact that the total number of ions in the solution increases on dilution, but the number of ions, right? But number of ions per unit volume that carry the current in the solution decrease. Okay, so this is the expression for the strong electrolyte. So lambda eq and lambda m are the strong electrolyte increase slowly with the dilution and can be represented by Debye-Huckel rule, and the slope equal to AB is obtained at the lower concentration as you saw in the graph. So this curve represents the strong electrolyte and this curve represents the weak electrolyte like the acetic acid. Okay. So for the strong electrolyte, moreover, the curve obtained for the strong electrolyte show there is a small increase in the this with dilution. This is because strong electrolyte is completely ionized in solution and so the number of ions remains almost constant. On dilution, the ions are far apart and therefore the inter-ionic attraction decrease and hence conductance increase and approaches a maximum limit value at the infinite dilution. It is also observed that the plot of the strong electrolyte become linear near the high dilution and can be extrapolated to a zero concentration to get the value of this. Similar for a weak electrolyte, at the same concentration, the conductance of the weak electrolyte is less than that of the strong electrolyte because the weak electrolyte are not completely ionized. Moreover, the curve for the weak electrolyte show that there is a very large increase in the conductance with dilution near the infinite dilution, right? And this is will represented like Collard's law. So basically, according to the Collard's law, the molar conductivity of an electrolytic at infinite dilution is the basically the sum of the molar conductivity of the ion present. For example, this is how we can represent, right? This is the conductivity of the individual ion. It means at infinite dilution, they are independent of the each other, right? And there no dependentiation takes place. So that is how we calculate the degree of dissociation. So for calculating the degree of dissociation, alpha of a weak electrolyte, then formula we use is like this. Alpha is equal to limiting molar conductivity at the concentration upon my limiting molar conductivity at infinite dilution, or we say zero concentration. So this is how we can actually calculate the degree of dissociation. I hope this is clear to you. So this is all we already discussed. Let's how will you calculate the dissociation constant? So you'll calculate the dissociation constant by using the formula. It is very helpful in determining the ionization constant. So you will calculate the dissociation constant by using a formula C alpha square 1 minus alpha, where C is the concentration and alpha is the degree of dissociation. So this is all about the electrolytic cell that we'll discuss. So we already discussed all the important term related to this chapter, right? All the important concept of this chapter. So just try to understand this thing, try to solve questions, try to understand the topic, try to understand electrochemical series, electrochemical cell, electrolytic cell, batteries. So some questions are coming from this topic only. So try to utilize the, utilize the this thing and try to learn as much as you can. Okay. So just revise the whole class that what we already discussed today and try to solve question on related to this topic on, right? So let's see you in the next class. Till take care and do this question. Okay.